Sir, hello.
Sir? Hello, sir.
Yes.
Oh, no. Oyan Chaudhary wants to enter. He has joined right now. Okay.
ঠিক আছে। Okay, so we can start the class. Oyan Chaudhary, you are present, no? Roll number 210. Oyan Chaudhary, কোথায় গেল? Absent. কোথায় দেখতে পাচ্ছি না তো। He is not. You should respond. I cannot see. Vishnu Mittal.
Present, sir.
Pratish Kumar.
Present, sir.
Pratish Kumar.
Present, sir. Present, sir.
Doipayan Pal.
Present, sir.
Deepan Chakraborty.
Present, sir.
Inayat Ali.
Present, sir.
Shubhankar Vishwas.
Present, sir.
Onaranya Das. Who is this Onaranya Das? He has not joined yet in the classroom. Yesterday I told to Sia, out of these two, he is not present. তাপস জয়েন করেছে দেখলাম, বাট অনারণ্য he is not present today also. Somadip Bhattacharya,
Present, sir.
Pritam Mitra,
Present, sir. Present, sir.
yeah. Aman Raj Mohta,
Present, sir.
Sandeep Kumar Sahu,
Present, sir.
Dipro Banerjee,
Present, sir.
Orko Bera,
Present, sir.
Suardo,
Present, sir.
Sopayan,
Yes, sir.
Ananya Ghosh. Where is Ananya Ghosh? Absent. Rishabh Hari,
Present, sir.
Tapos,
Yes, sir. Present, sir.
Indranil,
First of all, I
Swayam
am
Chakra.
showing you
Present, sir.
Swayam Chakra,
because
Yeah.
I am actually making these.
Sumir Kumar Gand, Samir Kumar, not present. Then Sayan Chatterjee.
Present, sir.
Okay.
Sir, Pratish Kumar.
कहाँ गया था तुम?
Hello.
Yeah, Pratish Kumar.
Yes, sir.
I called you. You did not responded. Okay.
Sir, I am responding. Sir, I think my mic
Sir,
is not
Oyan Chaudhary
working.
also, sir.
Okay, okay.
Sir, Oyan
Sir,
Chaudhary
my
also.
mic was not working.
दे दीजिए. Okay. So this fluid mechanics lab, we are going to start. It consists of some fundamental experiments on fluid mechanics, and the theoretical part of which already you have gone through. Okay. So just a minute. Let me mute. Yeah. Okay. So mainly here we are going to have those experiments related to some fundamental characteristics of fluid flow. And already in your classroom, I have posted the experimental videos. So we will be discussing one by one. So let us start with the experiment on pipe flow. If we call this as experiment 1, which is experiment on pipe flow. Okay. And for each and every experiment in our hydraulics laboratory, where all these experiments are being conducted, we provide a data sheet, or what we call as the laboratory sheet. So here, in this mode, actually online mode, we have prepared a data sheet. Which is adopted from the one which normally we serve, but it is being modified. As you can see on your screen, something like this is being circulated to each and every student. So this I will put in your classroom. Okay, so you can have this. You take your time and go through that. So we will be discussing. So as you can see, the experiment is characteristics of pipe flow. Basically, there are several experimentations on this pipe flow. So the name of the experiment is actually characteristics of pipe flow. where there are certain objectives. Each and every experiment, there are certain objectives which are written here. You can see to study the characteristics of laminar and turbulent flow. Okay, so this is objective 1. Then to determine experimentally the coefficient of viscosity, this we can say as objective 2. And the third one is to determine the friction factor of pipes. Okay, so this experiment is a lengthy experiment. I mean, as you can see, there are 3 different objectives which we will basically do by taking different data readings, and also there is a component of flow visualization in this experiment as well. So if we go one by one, if we first concentrate on the characteristics part, that is characteristics of laminar and turbulent flow, I believe all of you know what actually is mean by laminar flow and turbulent flow, right? I think no need for any discussion on that. Am I correct?
Yes, sir.
Yeah, so you know what is laminar flow and turbulent flow. Now, the thing is that experimentally, how we can able to study that characteristics. That means in case of laminar flow, the typical behavior of the fluid particles, if one wants to study, there are 2 ways by which you can able to study. One is if you can able to see the motion of the particles, and by creating the situation where the flow can be treated as laminar, and then if you can able to view the movement of the particle and then you correlate with the definition of laminar flow, so that you can see, yes, laminar flow is occurring. And from laminar to turbulent also, if you can able to see the particles, you can say that, yes, I have seen turbulent flow is occurring as per the definition of the turbulent flow. And also the transition from laminar to turbulent, what we call the transition flow. So that also can be thought of within the purview of this particular experiment, where this flow visualization part we can able to see how this flow visualization can be done, and from which one can able to identify the different flow regimes. The second way to study these characteristics is by having a certain relationship, theoretical relationship between the head loss due to flow. We know that whenever flow occurs, actually, there is going to be some loss in energy. That is what we call as head loss. So that head loss and the velocity, basically the average velocity, to say. So this velocity and the head loss is having a relationship, which in general is denoted as I equals to kV to the power n. Okay, so here, this relation that I'm trying to highlight, I equals to kV to the N for flow through pipes, where I is actually the hydraulic gradient. That is, hydraulic gradient means it is head loss per unit length, actually dpdx kind of thing. Okay, so so this actually you can, this H by L. L is the length of a pipe under consideration. That means over this length, the head loss is HF, if we call. So that is basically I. So that is sort of dpdx kind of thing. Okay. So this hydraulic gradient is related with the average velocity by means of this general expression I equals to kv to the power n. Okay. So if we can able to make a situation where the fluid flow is laminar, then transition, and then turbulent, and you can able to measure or evaluate the head loss over the length L and the velocity, and thereby you can able to get this relationship checked for laminar as well as for turbulent. Typically for laminar flow, this we know laminar flow is a linear characteristics, isn't it? So thereby this relation is expected to be linear. So I equals to kv to the power n. This n, that is the power of v, is index n is equal to 1 for laminar flow. So if we can able to measure or evaluate the velocity and the hydraulic gradient for different flow situation, typically for laminar zone, one can expect to have a behavior of I with respect to V as linear. Or in other words, if you can able to plot I versus V for laminar, you can expect to have a straight line if you plot it in a metric graph paper. And but for turbulent flow, this n is not equals to 1, it is greater than 1. And that actually indicates that this I will be having nonlinear behavior. So if we can able to evaluate I and V for turbulent flow as well, and thereby you can able to plot I versus V distribution, from where one can find out the value of N and K. Okay, so by that method or by that approach also, analytically, with the help of experimental support, we can study the characteristics of laminar and turbulent flow. So these are the two approaches that we do in order to study the characteristics of laminar and turbulent flow. That is basically our first objective of characteristics of pipe flow. Okay, so how this is being done, we need to understand, and for that actually some experimental setup needs to be there, and that is, you can see on your screen that the apparatus which are being used for this experiment are written. So those are the Reynolds apparatus, the very age-old Reynolds apparatus in your theoretical study. I think this perhaps you were made aware of what actually is Reynolds apparatus. Then the measuring cylinder, stopwatch, and thermometer. These are some measurement devices. Apart from this, we also have another measurement device that actually is part of the Reynolds apparatus itself. Okay. So, and so this is basically the different apparatus for the experiment, and let us move on to schematic diagram through which we can try to understand. And I mean, I am not going into video that is already there. I left it to you to go through it if you do not already, if you have not seen it already. I just want to, yes. I am going to explain all these. Okay, just have patience. Okay. So now in your screen, I think you can able to see what we call as the schematic of the experimental setup of these Reynolds apparatus. I mean, this is actually not the Reynolds apparatus, but the entire experimental setup what we are having in our hydraulics laboratory. I mean, the setup has been design diagram has been drawn more or less inconsistent with what exactly we are having in our laboratory. Okay, you can also while going through the video, which actually was shot in our the separate apparatus what we are having. Okay, so here you can see that first of all, we need to understand that we have to create a flow situation, flow of water. Water is our fluid here. So water has to be directed in a particular direction, or it needs to be moved. I mean, the water should have a motion, fluid motion. The motion of water has to be there, and we need to create a situation due to which water should be able to flow through a circular conduit or a pipe. So we are having a glass tube, as because, I mean, as I said, that the flow visualization part is also there. So we are using a glass tube as because it is transparent, you can able to see. But at the same time, water is transparent, so particle visualization is not possible for water until and unless you color it by some means. Okay. So the thing is that, I mean, if I want to visualize the flow, the motion, and that too for water, I need to do things. First of all, so that water should have a motion, and then we need to also colorize the water particles, or to add something so that we can able to see the motion of the particle of the water, or some additional compound which is carried with the water, so that we can say yes, water movement is like that. Okay, so this is the idea actually. So in order to create the motion situation, you need, we know that any fluid will flow once you have a difference in head. Okay, so the total head actually. So you need to have a potential due to which it should start flowing once you have the passage open, flow passage open. In order to create that head, actually, a tank is being used, number 3. That is basically the tank, which is denoted here as constant head tank. Okay, so this is the tank I'm highlighting. Okay, so by water from supply. Here, supply means this particular setup is mounted, I mean, located at the ground floor of our hydraulics laboratory. And from over a tank, actually, this particular constant head tank, which is basically mounted at some height from the floor, in the ground floor itself. And this is being filled up by the overhead tank, which is above the roof. So through some pipe lines, and that line actually you can follow. The line is coming in this manner, some U, and then it goes to the tank, constant tank. So in between, I mean, there is a valve too. You can see the symbol of this valve. So this valve actually is being used to fill the overhead tank, this constant head tank. Okay, 3. So the moment, and this should be within the reach of the personnel who will be conducting the experiment, or if you are going to conduct it, you should have this access to the valve. So that's why actually the pipeline comes down to a level where it can be accessed, and then again it goes up, and then it enters into the tank. Now this tank is having a special feature. It is basically having two chambers inside it. So tank is basically a container, closed container, inside which there are two chambers. That means it is having a separation inside. A separation wall is there, which is schematically shown here. So this is basically that wall. So the tank, this part actually is being filled, and then once this height is achieved by the water, the excess water comes to the second chamber, that is this chamber. Okay, and this chamber is connected with an outlet, this outlet, which actually goes to drain through another valve 14, you can see. Okay, so this actually goes to drain. The reason of having this particular type of tank is to maintain the head available for the flow of water constant. So if you now look into this chamber once again, that is the first chamber which is being filled by water. The moment you have this level constant, this level achieved, and then excess water is coming here, and through this line when it comes out, and which actually comes out to drain, which is visible to the personnel or to us actually, that water is coming out from the line. So these actually indicate that you are having this tank, that means the chamber active part, the usable chamber, has constant. Can we say that? This part, when you see that water is coming up through the drain line from this tank, we can say that yes, it is ensured that the tank, usable part of the tank for the experiment, is now at constant head. আমরা এটা বলতে পারি? Okay. So that actually is starting point. That should be the starting point of the experiment. Means you have to open the valve 2. That means the supply line, and then this tank will start filling up with water, and then you should open the valve 14 so that you have the indication that the tank is being completely filled up. And throughout the experiment, you need to have this water coming out from the tank, that if you want to conduct the entire experiment for constant head, then the condition is that always it should come out through this drain line. That means, of course, the supply, this supply should be having a much higher flow rate than the flow rate with which you will be working with, right? So that is a precondition. Okay, so once this particular head is ready, then we can look into the main part of our setup. That means you can find another line coming out from the main chamber of this constant line head tank, and then this line actually goes through another valve 13 to a chamber, and this chamber is having some components inside. This is an important chamber actually, which is basically kind of a cylindrical in shape, like pipe, but it is having a larger diameter than the pipe through which we are directing the flow. It means this pipe actually I'm talking about, this is the glass tube. So this part is also another cylindrical part, but having a larger diameter, and both the end of this cylindrical part is being closed by corks. Okay, so these are the corks having holes through which the glass tubes are being inserted. So this is one portion of the glass tube, or the inlet pipe actually coming from the overhead tank, and this is another part which goes inside the chamber. So this is basically the outside outlet of this chamber, which is known as the settling chamber. Okay. The settling chamber, you can see this is here 7. Number 7 is your settling chamber. So where from the overhead tank through valve 13 flow enters and it fills up this chamber. So this chamber is having one inlet, one outlet in the direction of flow, as you can see, as well as it is having two other outlets or opening in the normal direction, or at the normal direction means I'm talking about this one, right? Where you can see one line. I mean, this line, if you see, this actually is coming from another container 6. Another container 6, which is situated slightly above constant head tank, and this container actually is having colored substance. Typically, we can say we are having, say, KML. What is KML4?
Potassium permanganate.
Yeah. Potassium. What is the color of potassium permanganate?
Violet pink.
Violet pink. Right. So that this actually is the dye. We can call it as a dye. So this 6 is a dye container which will have the substance, a colored substance, typically will be used to colorize, to basically, so from this dye container, a line comes out once again. This is a smaller diameter line, and then it enters into the settling chamber. And at the outlet of this particular line, we are having a nozzle. Okay, so this is basically being symbolized. So through this nozzle, actually, the dye will come and it will mix with the water. And the mixing actually will be started, or the dye is allowed to mix. Once you have this pipe, that is another, it's a kind of a pinch valve or a cork valve. If you rotate it, then this particular pipe, which is a flexible pipe, I mean, this is just actually this valve, press the pipe and the flow can be stopped. So if you rotate the screw, then it will basically unpress the pipe and thereby the flow of dye will occur. And this is just, due to the gravity, it will start falling. And here there is no question of any, maintaining constant head or something like that. If you emptied this bottle, again you need to fill it. And so that's the thing. It is just to mix the dye particles with the water. So typically the main motion of the water, it will carry the dye particle with it. Okay. So this nozzle, actually, this is the dye nozzle, and just beside it, number 1, actually, you can see there is another outlet which we call as the vent line, and it is having another valve here. So basically, to start before starting the experiment, one needs to make sure that this entire passage of flow should be having a single fluid, that is water. Okay, there should not be any mixing of other fluid. That means the possibility is that you can have a air inside the air entrapment inside the passage. Okay, so this air should be released, and you should have complete water throughout the volume of the passage. Okay, so to ensure that, the topmost point, we are having a vent line. So this valve needs to be open the moment you have water flowing through this from this constant head tank to this settling chamber. It goes to the test section. So all the lines And if there is any bubble identified within any portion of the passage, that has to be directed towards this vent line and it should be released, so that you can see that there are no air bubble inside the test section or somewhere else. Okay, so for that this vent line is used, and once you see that it is completely free of any air bubble, then this hull needs to be closed so that no air can able to come inside, right? So that is basically the preparation part I'm talking about. So which then after you make this entire flow passage up here, then you can say that my experimental setup is now ready. Okay, so one can see that this is basically a larger cross section where the flow water comes from the overhead tank, tank, and then this mixing of particles is basically being done by re-entry means of a converging nozzles of section. So this is entry the water into the test section pipe, okay, from the settling chamber, and this shape is like a bell, and that is why it is called bell mouth entry. So number 10 is bell mouth tube. You can see it is written here, bell mouth tube, or it is basically the bell mouth entry. So that actually, I mean, here it is a convergence that created by providing this kind of a guide, so you can have a flow to become uniform. Okay, and so after this bell mouth tube, there is a constant diameter glass tube, and that actually is going towards our test section. So now we can identify test section, means where we need to concentrate. That is this L, that is this length of glass tube. This length of glass tube actually where we need to concentrate, or which is our main window where we are going to visualize as well as the measurements of the head loss we need to take. Okay, so here in this glass tube you can identify two tappings. Okay, and one R and one L in small letter, small r and small l is written, that is right and left. Okay, so which are connected, these two tappings are connected by means of a flexible tube to a device here. This is basically another measurement device which is not listed in that particular apparatus because this is part of the Reynolds apparatus. Okay, so this is basically a U tube, glass U tube, which is mounted inverted U, you can say, and the two limbs of this U is having scale fitted with them. So this scale you can able to see. So typically this U tube is filled with air, and when occurs through this tapping, flow will come to the respective limbs, and because of the loss, one can expect to have difference in the meniscus of the water inside the U tube, and this the difference in the two meniscus will give us this head loss. Okay, here it is denoted as HW. Okay, that you understood? You think? Okay, so here also having a vent valve, I mean um, to insert, I mean air, if by some means if it is completely filled with water. So why we are using inverted U tube? I mean, this is basically a manometer, inverted U tube manometer, and different types of manometer. The simple U tube manometer is the one that is oriented like an U. Then it is the inverted. Why inverted U tube we are using, and the manometric fluid here is air, because the difference in head between the two tappings are very small. So if you use high density manometric fluid, you may not able to distinguish the difference in the head, because that difference will be very less. So if you use a lesser density manometric fluid, then possibly you can able to get the difference in reading. So it's a manual observation. So the reading needs to be taken manually. So that's why you have to select the appropriate pressure measuring device. It's basically pressure measuring device in terms of head difference. You get it, and that actually gives us delta P, or the DP part, right? Or you can say DP star. Okay. Here, if the tube is horizontal, so we have to ensure the tube is horizontal. So there is no such elevation head reflected in the manometer. I mean, how that can be ensured that it is being perfectly horizontally mounted. So for that you need to have some kind of spirit level to be placed, and then check whether at different points the pipe shows the same rating of the spirit level. Okay, so to ensure the pipe to be horizontal. So if it is horizontal, head difference will only be the head loss friction, that we can say. Okay, so this inverted U tube manometer is inverted U tube manometer 12. You can see it is also written here. It is the inverted U tube manometer, which is being used to evaluate the loss due to friction over L. So if the knowledge of L is there with you, and you can able to measure, you can able to take the reading to by the difference, you can find out what is your I, which is as per this notation is W by L. Okay, and so this part we can find out by using this measurement device, that is our inverted U tube manometer, and to get the inside variable part, that is the Q, that is the independent variable Q. So that Q means is the discharge or the flow rate to the pipe. So as you can see, this glass tube is having a bend. I mean, here this part, I mean here this part actually is a rubber tube connection, which is being bent, and then it is basically having an outlet to the atmosphere through another valve 4. So this is the valve. If you change the opening of this valve 4, regulating cork in water line, as it is written. So to regulate this one, you actually can able to regulate the flow rate. Okay, by changing this area of opening, you can change the flow rate. So thereby, you can have different flow rate for different opening as you are maintaining. So thereby, you can able to change the flow rate under constant head. Okay. So once you're able to change this flow rate, you should be able to find out how much is the flow rate coming out through this pipe. So we need to measure by means fundamental this one is the measuring cylinder where if you collect the water coming out from through this particular tube for a given amount of time, if the flow is steady, this is the condition. If the flow is steady, then the volume of water collected over a period of time will be good enough, we can say, to give us the information about the flow rate, isn't it? Because at steady state, we can, as I say that this Q is equal to volume of water collected over a period of time T. Can we say that? Okay.
Yes.
So this is the flow rate which we can evaluate. If we can able to collect water volume in a measuring cylinder over a time T, okay, and then we need to note down the time of collection and the collection of water which is being collected in the measuring cylinder. So this measuring cylinder is having a graduation, you can see, so you can able to measure the height of water collected, and then if you know the cross section of this cylinder, you can find out the volume, right? So the steady state flow rate, you can able to evaluate. But our point of interest is not exactly the flow rate, but the velocity, average velocity v. There is this one. So if for steady state, now you need to use the steady state continuity equation in integral form. That means we can write Q is equal to AV, right? This is our steady state relation of the continuity equation, correct? Where this A is the cross section of the pipe, we can say that is pi d square. I mean, here, inconsistent with the notation used, it is actually pi capital D square by 4, right? So basically, if you know what is the diameter of the glass tube, of course, it should be the inner diameter of the glass tube, then you can find out from the knowledge of Q what is the average velocity V. So I and V now is known to you for a particular setting. Setting of what? Particular setting of this opening of the valve 4, right? So for a particular opening of this valve 4, you can able to find out this I and V. Now, what is actually done? We start from the situation where the drain flow has been started, and the drain flow has been started, and so this drain flow has been started. That means it is ready, and there is no air bubble inside the entire flow path. Okay, that is number 2, and then at that point of time we need to close this 4 entirely, so that this complete chamber, the flow passage, everything is filled with water. And at that condition, when you completely close this valve, what will be the reading one can expect in the manometer? Or in other words, what will be your value of this HW when I close this valve 4? What will be the value of HW at that situation? 0 হয়ে যাবে, because it is at static condition. Some flow type, as there is no flow, there won't be any loss of head, right? So one can expect the two meniscus at same level at that point of time during when your valve is this number four valve is closed. Okay, so that is my zero condition or the starting condition, and then we will open the valve flow 4 very slightly, a little opening. Okay, after opening that, and then we will open valve 5 so that the dye will start mixing with the water, and we want to observe how the dye particles are flowing. Typically at this portion, that is our test section. So this is actually my test section. Okay, this is the test section. So I need to observe the flow of dye particles. Okay, basically what we are observing here is the strict lines, we can say, because these which, if you can recall the definition of the strict lines, it is the motion of the particles which actually has a common emerging. Okay, so basically that through from where all the dye particles are coming out, right? That we can. So all the dye particles are coming out from this point, and then it is carried by the water through this conduit. So how they are behaving within this chamber, or in a broader sense within this entire glass tube, this visualization can now be done, because you can able to see that, as you have said, that KMNO4 is having a violet-like color. So one can expect to have the flow visualization possible. So, and at the very beginning, when you have very small opening of the valve 4, you can expect to have a thread-like motion of the dye particles in a straight manner. If the experiment is done by maintaining very very stringent ambient situation, that means this flow can be disturbed, external disturbances. That means that could be some sort of vibration, okay, and that could be some sort of misalignment between the different connections. So you have to maintain all those things so that you can have the view of the dye particles in a perfect straight line manner, as typically one can expect for a laminar flow situation. Because we know that in laminar flow, the particles move in a straight parallel manner. So if it is like that, then we can say, yes, the flow which is occurring through this glass tube is laminar. And if it is like that, then you need to complete the recording of the different readings. That is, you need to take this both right and left limb reading in the data sheet, and then you need to start the time to take the volume or to start the collection of the water volume using the measurement cylinder. So some personnel has to be there who will maintain this time by using a stopwatch, and another one should immediately after the command comes start, then you have to place the measuring cylinder below this pipe so that you can start collecting water, and the moment the command comes stop, you have to take out this measurement cylinder and you place it at a flat surface and take this reading. Okay, so the time recording and the volume of collection, this should be done in a synchronous manner. so that you then calculate Q, and from Q you will get V. So that will complete one set of reading, including the visualization. That means whatever you observe, that also you need to note down in your laboratory sheet, that what is the feature of this dye particle, whether it's straight line, or whether it is wavy, or whether it is completely diffused. So if you see it is like straight line, then you write straight line with that is your observation, along with those measurements, recording. So after that, you need to change this number 4 valve slightly open further. Okay, so from minimum opening to the next one, and then you need to repeat. You need to see whether still the dye particles are being carried in a straight manner, and that means it is a straight like thread. So again, your observation should be straight line, and you need to repeat the measurement of right and left for the manometer, and the time needs to be again restarted, and you have to empty this measurement cylinder and then again start recollecting for another, say, 15 second or 30 second, whatever you set. Okay, so that will be your second observation. So in this manner, you have to change this valve opening, and you observe the motion of the dye particles. So after certain opening, you may find that this straight line motion is no longer maintained. Rather, the dye particles are moving like a wavy threads. Okay, so that actually signifies that we are moving from the laminar regime to another regime. So it can be attributed as the transition zone if you observe the motion like that. So the moment you have that type of dye particle motion or the straight line in a wavy manner, again you need to hold it at that particular condition and take the readings. That means again you need to measure the volume of water collected for a time period, and then this pressure difference in the manometer reading. And after that, again you need to increase this valve, and for say 2-3 readings, after 2-3 settings, you may find that is now the waviness also have gone, and the entire glass tube is filled with the dye particle. That means instead of water, you may find that it is a colorized liquid, as if flowing through the pipe. So that actually indicates the flow is now in turbulent zone, because we know that in case of turbulent, there will be abrupt mixing between the particles that takes place. So, and because of that, the dye particles are completely diffused in water, so that it's a complete mixture of dye and water. You cannot identify or you cannot able to distinguish the water and dye separately. Okay, so under that situation, if you go on increasing the opening of the valve further and further, you can only have more and more turbulent flow occurring. So some more data are being taken by opening the valve further. Some few data are taken, and that actually completes the flow visualization along with recording the data for post-processing or for further investigation or for the further study in analytical manner. Okay, so this is the experimental procedure that we do for this experiment on pipe flow. Okay, so if you understand up till this point, Okay, if you have any query, you can ask, or else we then move into the analysis part or the post-processing part, how those are being done, and and the other two objectives, how those can be completed. Okay. Now, ওটা initiate basically এটা depend করছে, I mean from experience, when the flow rate is very less, I mean very low flow rate, that is why at the beginning part I think you have seen that it is 15-second duration, but at the later stage, when the flow rate gets increased for turbulent flow, you need to increase the time duration, okay, so that you can have, because you are doing it manually, okay, so if more time if you provide, okay, so you can have the collection amount to be more, so that you can have a calculation or the reading in a proper manner. Okay, that's why a significant amount of time should be given, so that the collection of amount or collection of water should be substantial. So it can be 10 seconds, it can be 20 seconds, but it should be maintained. If it is 20 seconds, I mean the stopwatch should be stopped at 20 seconds and not 18 or 21 or 22 seconds. So that actually results accuracy in the analytical findings supported by experimental data. So those actually may create error in the findings. Okay, those are human errors, you can say. And also, it is more important to maintain the synchronization. I mean, the moment you stop the watch, simultaneously the measuring cylinder should be completely released from the water supply. Okay, which that means you need to take it out immediately when you stop the time recording. Any other question related to the experimental setup? If you have, you can ask. Okay. If you do not have any query, then what? Then the visualization part is over. Now we need to come to the study with respect to this I and V relationship, as I have said at the very beginning, I equals to K B to the power N. Okay, so something like this. This is the sample data for you, as because you are not able to participate physically in the experiment. So as if we have conducted the experiment in the video which is shown. So these are the appearance of colored jet you can see. So you need to write in this way: straight line, straight line, straight line, and then say from 6 run number, the behavior of the dye particles is like wavy. So 6, 7, 8 is wavy, and then 9 onwards up to 14 you can see all are diffused. Okay, so these are diffused. This indicates, visual impression is that the flow becomes turbulent. And correspondingly, you can see the time, all are 15-second duration, and the collection amount, how it's changing. So it starts with 20 ml and then it goes 410 for 15 seconds. So that indicates the increase in velocity, and these are the manometer reading. And the difference is in centimeters. So the difference is very less initially, and then gradually it increases. So these are the primary recording of the experimental data, and then you need to find out the volume in meter cube, that is this one, and the flow rate, as I said, that is Q equals to volume by T. Here it is denoted as omega. I have written like this. So anyway, both are same. So that is the volume flow rate, and then you need to look into this column, that is the gradient, hydraulic gradient I, HF over L. So for that you need to know the value of L, that is the distance between the manometer tappings, which is shown here. This is the distance between the manometer tapping and the seat itself. Is 99 centimeter, is about a meter actually, and the internal diameter of the glass tube in the above line, it is also 7 millimeter. So once it is known, you can find out the cross section area of the pipe. So that you need to write down here, and some other parameters are required. That is temperature of the water, you need to measure. Density of water you need to write down, and the kinematic viscosity of water. These two actually you need to write down using the property table. Okay, in our laboratory, property table of water is furnished in the notice board. So after measuring the temperature, you have to consult this property table, and these two density and kinematic viscosity value you need to put up here. The reason is we also know that in order to characterize this laminar and turbulent flow, non-dimensional number is used, which is none other than our Reynolds number, which is for pipe, it is rho Vd by mu. So in order to evaluate this Reynolds number, as you can see, it is in the last column here written. To get this Reynolds number, you need to know the diameter of the pipe, you need to know density, viscosity, and the velocity. Now, this average velocity V actually you are evaluating by the knowledge of the flow rate Q and the cross section. So this will give us V, but the density and viscosity you need to find out. And that for this particular objective, it is being obtained from the property table. So kinematic viscosity, if you know, I mean that is the same. Basically, it is Vd by nu. You can also write. It is Vd by nu. We know that is kinematic. So straight away from the kinematic viscosity value, you can find out the Reynolds number knowing this velocity and the diameter. Okay. Okay. So this table can be completed, and then what has to be done? For that actually, I refer. I mean, we'll come back to this. So some supporting snapshots are also provided in this document. I think you can go through that. Whatever actually we have discussed, I mean, those important aspects are being provided here. And this is the die feature to the straight line laminar, this is the die jet one can expect to see. And then this waviness, I mean, this is the diffused one. And the wavy one is a bit difficult to identify through these static figures, snapshots. I mean, it is a bit difficult. I think I don't know whether you can manage to identify or not. But while observing the video, probably you can able to see those waviness. Anyway, okay. So let us move on to the what to do with this I and V, that actually you need to plot in a log-log graph paper. That means basically in log scale you need to plot. Now, I don't know whether you are aware with this type of graph paper. Typically, what the graphs we normally plot is in a metric graph paper. Means where the graduations are in metric scale, right? But
Yes.
Instead of metric scale, you can have the graduations or the divisions which are in log scale, log base 10. Okay, if that is the graduation, so that we call as log-log graph paper. You can have log-log means both x and y axes are in log scale. So the benefit of using that type of graph paper is that a nonlinear behavior can be seen as a straight line in a straight line or linear manner the moment you are using this type of a graph paper. The thing is very simple. You can understand. Say we are talking about this relation I equals to kv to the power n. Now, if I take log both sides, it becomes log I is equal to log k plus n log v, right? Like this. Is it correct?
Yes.
So, that means this we can think as y is equal to this as some constant c plus this as isn't thing as this is log v is x and n as mx. So it is y equals to mx plus c, right? So if you take log of I and then this log k and then log of v, or basically you are having here the known things are I and v because these you have evaluated. Your objective here is to find out k and n. These two are unknown to you. So how to find that? If you plot this I and v or log I and log v in a metric graph paper, then you can probably find out the index n and the constant k. Typically, one can expect to have two regions, two distinct region, one for the laminar, that is something like this, and the other for the turbulent, which is something like this. Meaning, you can see those crosses, which are the points actually, which are distributed here. Okay, so these are the different points. So for laminar region, you can expect to have a point distribution like this. So the first 1, 2, 3, 4, 5 points in your sample data where you have found the straight lines as the observation, visual observation, and if you put it in this graph paper, either by taking log of that and then plotting it in metric graph paper, or if the scale or the graduations are itself in log scale, then you need not calculate the log of those variables, those values. Okay, so the graph paper will take care of that. So that is the advantage of using log-log graph paper. Okay, so once you have this distribution of points like this, and the others, as you can see, so these are the other points. These are the other points. I'm highlighting those which actually shows to distinct feature. So, and then these are the other 3 points. Okay, so all the points, first of all, you need to put it in a graph paper, either log or metric. If it is log, you need not convert those values into log. If it is metric, you need to take log for those values. Okay. So once you have the distribution, then you need to identify up to which point you can have a straight line to be drawn. And possibly the best fit line, actually. I mean, not passing through all the points, may not be possible. Okay. So that we have tried to do here. You can see this regime where these red points are there, and more or less giving weightage, same weightage to all these points. You can able to draw a line, the straight line, okay, up to this. And then there is another region here, this green circle points. But again, by considering these points, one can able to draw I estimated best fit line. So these are the 2 lines, straight lines in log scale, which we can say are the representations of the 2 distinct regimes. That means this will be my laminar regime, and this onwards here can be attributed to turbulent regime, right? And in between this zone, we can say this has to be transition. Getting my point? So in a graph, actually, you can able to represent the entire flow regime in terms of this I and V. This is the first, you can say, the significance of plotting I versus V. The second one is to find out the value of this K and N by using these 2 different straight lines. That means you are going to have for laminar one set of K and N combination. For turbulent, you will be having another set of K and N combination, isn't it? So once you draw this straight line, then on this straight line you can take 2 points, right? Say 1 and 2, these are the 2 points. And then you can write here the equation once again as log I1 is equal to log K plus N log V1, and then log I2 is equal to log K plus N log V2. So these are the 2 equations, solving which you can find out log K and log N. So solving this, you get log K, from which K can be evaluated. So K and N value for laminar you can find out. So this is only for laminar. In a similar manner, for turbulent, that means your I3, V3 set and this I4, V4, as it is mentioned here. Okay, this will be for this you can use for the turbulent region to find out your K and N. Right. So one set of K and N for laminar, one set of K and N for turbulent. To check whether for laminar you are having N 1, N is equal to 1. If you have done the experiment correctly and if you have plotted it properly, then one can expect to have n as close as 1 because it is expected to have I equals to kV with the index n is equal to 1 for laminar. But of course, for turbulent, it should be greater than 1. So that is the way by which we can have this analytical part completed, and we can say the study of the characteristics of laminar and turbulent flow gets completed. So that is the objective 1. Okay, and that is the major part actually. So once you complete this objective 1, then you are left with the evaluation for the second objective, that is basically to find out or to calculate, to determine viscosity experimentally and compare the value from standard table as stated next to the. We can revisit this page where it is mentioned to determine experimentally the coefficient of viscosity. So this is going to be our second objective. Okay, to find that experimentally, already as you might have observed that in order to find out the Reynolds number, we need to know the viscosity, isn't it? And that we have used by consulting the property table. Okay, but experimentally you can also find the value of viscosity using the well-known equation which is valid for laminar flow only. So that is our Hagen-Poiseuille equation. So using that Hagen-Poiseuille equation, you can able to find out this viscosity. So what is our Hagen-Poiseuille equation? I think you can recall that is Q equals to, as it is written here, pi d to the power 4 over 128 mu, where mu is the viscosity, right? And with rho g hf by L. So this is the complete form of our this thing, Hagen-Poiseuille equation, which is for laminar flow only. So for and that should be written in terms of the average velocity as well, pi d square by 4 into v, right? So this is the Q. So if you now for laminar region I V versus I and get a point on line, write this expression, I mean this Hagen-Poiseuille equation in a modified manner in term as mu is equal to the rest. That means you can write this as pi d to the power 4 rho g hf by L I can write as I, right? And then 128 Q in terms of Q. Victory. This you can write as pi d to the power 4 rho g I and 128 Q এর জায়গায় লেখো pi d square by 4 V. So you get some simplification, d square and here it will be d square. So altogether it becomes, and this 4 means 32. So it will be d square rho g I over that is mu. So here from this V versus I plot, as you see, you can have this I and V at any point on the straight line, you consider, and you get this I and V, and for that you can find out this mu, and you can check it with the one that you have consulted for the temperature of water you record it. Okay, because we know viscosity is a function of temperature. So this is the one which you can able to find out for using Hagen-Poiseuille equation, and you can compare it with the property table. So for that, I mean, the prerequisite is to identify the laminar zone, because the data that you will be using to plot this V versus I in metric graph paper. Here it is, I mean, there is no necessary to plot in this log graph paper. The precondition is already as if you have identified the laminar zone, that means your index L is 1. So for that region, the values, the points that you have obtained can be treated as laminar flow data. So for those data, you now plot a straight line, the best fit straight line, and on that straight line, you take a point and find the value of viscosity from Hagen-Poiseuille equation. So the evaluation of viscosity will only come after the previous one, that means after identification of your laminar region. Getting my point? Okay, so this is about the second objective, and the third one is basically another application. That is the application of to determine the friction factor for pipes. To determine the friction factor for pipes, that is our third objective. And actually, previously it was two different experiments. As such, we don't require any new experiment to get this particular friction factor evaluation. Here, for the evaluation of friction factor in pipes, we assume the pipe to be hydraulically smooth. That means we know that friction factor is a function of your Reynolds number and surface roughness. It is basically a function of Re and epsilon, where epsilon is the relative roughness. Okay. So for that, actually, we only need to use the data that already we obtained in our previous experiment. That means only one experiment actually here, where we have already identified the two zones distinctly laminar and turbulent. So this is the table. You can see calculation of friction factor for laminar and turbulent flow only. We are not going to calculate the friction factor for the transition zone. So you need to pick up those runs for which you got the laminar region and turbulent region. In between the points, how many points? I mean, maybe 3 or 4 points. Those data you need not use here. Okay. So for friction factor, we have a experimental obtained equation that is called Darcy's equation that we know. You can recall this Darcy's equation, where your head loss is being related with your diameter, with the length of the pipe, and the average velocity. We know this HF is equal to FL by D, V square by 2G. That is, so from that V square by 2G. So from that we can write F in terms of HF, L, D and V square, isn't it? So just by rearranging, you can have an expression of F. That is basically, we can say, the experimentally obtained friction factor. So here in the table, you can see that is being denoted somewhere here in this column. You can identify this one I'm highlighting. So F is equal to HF by L V square, L by D V square by 2G, and within bracket it is written as EXP. This is basically experimental. Why we are calling this as experimental? Because Darcy's equation itself is, we know, is an equation obtained from experimental finding only, isn't it? If you can recall the genesis of this Darcy's equation, it actually came from experimental observations. Okay. And F is just basically the constant, proportional constant, and from where it is coined as friction factor. So anyway, so that is why this expression is we denote as experimental, and this relation is valid both for your laminar as well as turbulent flow. Okay. And but however, we can have the relation between friction factor and Reynolds number in laminar flow, and we can also have a relationship between the friction factor and Reynolds number for turbulent flow using certain theoretical means combined with this experimental or Darcy's equation. In case of laminar flow, if you combine your Hagen-Poiseuille equation with Darcy's equation, you end up with this relation F is equal to 64 by RE. This one. I think possibly you have done in your fluid mechanics 1. You can also do, revisit that. That's very simple. I mean, just to combine these two, you get F is equal to 64 by RE as the relation. It is for hydraulically smooth pipe, or, in fact, for laminar, it is the same relation. And for turbulent, actually, by Blasius's equation, we can get a relation of F and Reynolds number, and that is written in this manner, 0.3164 over RE to the power 1 by 4. So this is from Blasius's equation for turbulent flow. Okay. So now the thing is that means we need to find out friction factor using Darcy's equation. So this column will be entirely filled up for all the data that you will bring it here for laminar and turbulent. You should not bring the transient data here, right? So this column will be completely filled using Darcy's equation for all laminar and turbulent, and for laminar region only, maybe say up to this you are having laminar region. So up to this, using this F is equal to 64 by RE, it will be filled up. And for the remaining part, that is for the turbulent region, here you need to fill up. Getting my point? Okay. So, and of course, your Reynolds number is you have already calculated from the earlier exercise, and then you need to plot F versus RE in log-log graph paper. Again, here you need to plot in another log-log graph paper as it is written here. So this you need to plot in a log-log graph paper, because you see both this relation F is equal to 64 by RE and F is equal to 0.3164 over RE to the power 1 by 4. Both these relations are nonlinear relations. So in order to have it in a linear fashion, if you take log on both sides and then you plot, you will get straight line. Or else, if you have a graph paper which is having its graduation in log scale itself, so only by putting the points, by putting the values actually, you see it will come like a straight line. So one can expect to have a behavior something like this. This is for the laminar part, and this may be for the turbulent part. So this is the F is equal to 64 by RE, and this will be F is equal to 0.3164 over RE to the power 1 by 4. So this is F and this is my RE. But both the scales are in log. Okay. It is a log scale. And you will find cycles. I mean, because if the base is 10, we know that every, in terms of order of, 10 to the power 1, 10 to the power 2, the same behavior will be repeating, isn't it? So that's why actually you can start, the origin should not be 0, it may be 0.1 or 10 or 1. So if it is 0.1, then the second one will be 10, and this 0.1 to 10 may be graduated, and you can see a variation. That means it is not uniformly divided, and the next cycle will be 100, and the next one will be 10 to the power 3, something like that. So it will be 0.1, 10, or you can start from 0.01, then 0.1, then 1, then 10. Okay, actually I have missed it. It should be 1, 0.1, then 1, or else you can have 1, and then 10, then 100, something like that. Okay. In a similar manner, the y-axis has to be chosen like that, depending on the range of data that you have got, right? That you have got. Okay. So accordingly, you can choose your starting point and the end point. Okay. Now the thing is that if you are going to use Excel and some software, either MATLAB or Excel, to plot, you can find that there some log scale is available. There are options in which you can choose for metric scale, or you can choose for plotting in log scale. So by using a software, you can straight away plot it. But you need to do it, I think, if you're using software, you plot in metric scale and you plot in log scale to check the difference. Whether these linear behaviors are coming or not for the log scale. Okay, so, just to complete this exercise, here you need to also put the points that you got using Darcy's equation. So these are the two lines that I have drawn for the two equations. So straight away, it is obvious that it will be looking like this, but you need to put the points about these lines which you may got from the Darcy's equation, applying Darcy's equation. So those may be distributed like this. Okay, so this is about the evaluation of friction factor for pipes. Along with that, for the laminar turbulent characteristics, you have to identify the critical Reynolds number, as it is mentioned here, which I probably missed to mention. Okay, so the critical Reynolds number, how you can able to obtain it? For that, you need, once again, you need to use this plot, right? So this I versus V in log graph paper. So after you got these two straight lines, you need to get an apparent intersection. That means by projecting this line and this line, okay, you need to get an apparent intersection. And through that intersection, actually, this is going to be the apparent intersection. And you need to drop a perpendicular on the x-axis, and which actually will give you a point of velocity, which we denote as a critical velocity. In actual situation, if you go on increasing the velocity, one can expect to have a lower critical Reynolds number and an upper critical Reynolds number, depending on the manner you are changing the conditions. But here, as we are doing it in one direction only, it is a simplistic way, you can say, to obtain a critical velocity, and the corresponding Reynolds number we denote as critical Reynolds number. So Re critical will be your V critical d over nu. Okay. So these you need to write down in your report and how you have obtained it. So and you need to show it in the graph also. This is the way by which you have located the critical velocity. Okay, so this is about the entire experiment. If you are having any query, you can ask. I think after this discussion, once again, I request you to go through the video. I am not going in through that video because that is after having the understanding, I think you can able to now understand what actually is being done in the video. And the data is with you now. I will be putting this document in the classroom so that you can start doing the post-processing part. Okay.
Yes.
Okay. Any questions you are having, you can ask. No query. Okay. So that is about the first experiment, we can say. And let me stop the presentation. The timing. Yeah. So you start doing this post-processing part. I mean, I will be posting this document, Word document, and you start doing. So next day we will be having another experiment related to this viscosity, the Stokes law, and then we move on to calibration. Okay.
Okay, sir.
Okay.
Okay, sir.
Yes. কি আছে তোমার কি দিয়েছি চারটে বলো তো আর কি আছে ছটা এই অ্যাক্সিসিমেট্রিক আর রোটামিটারের অনলাইন করানোর মতো মানে মেটেরিয়াল ল্যাবে তৈরি নেই ঠিক আছে ইনফ্যাক্ট রোটামিটারের সেট আপটাই বোধহয় রেডি নাই মানে ইন ফিজিক্যাল সেন্সে ওটা করানো যাবে না তবে অ্যাক্সিসিমেট্রিক যেটা হয়তো মানে যদি ফিজিক্যালি তোমরা আসো তাহলে করিয়ে দেখিয়ে দেওয়া যাবে বাট ওটার কোনো ভিডিও করা নেই ওটা ভিডিও কারণ ওটা এয়ার বেসিক্যালি অ্যাক্সিসিমেট্রিক যেটা হচ্ছে এয়ার নিয়ে এবার সেইটার ভিডিও করে মানে এয়ার তো দেখতে পাবে না কিছু হ্যাঁ ওখানে স্মোক নয় অ্যাকচুয়ালি কোনো যে ওটাকে ভিজুয়ালাইজ করা যায় না এটা একটা নজলের ভেতর দিয়ে এয়ার ব্লোয়ার দিয়ে পাঠানো হয় তারপরে তোমার জেটের মেজারমেন্ট পিটার টিউব দিয়ে করা হয় ফলে মেজারমেন্টগুলোর ভিডিও হয়তো করা যায় কিন্তু ওটা ঘটনাটা কি ঘটছে মানে হাওয়া তো দেখতে পাবো না আমরা ফলে ওটার ভিডিও করতে গেলে ইন অ্যাডিশন টু দ্যাট উই নিড টু ইনজেক্ট সাম ডাই মিনস স্মোক তৈরি করতে হবে যেটাকে দেখা যাবে ভিডিওতে ফলে ওটা করা সম্ভবত হবেও না আর বিকজ এখন আস্তে আস্তে তো আমরা অফলাইনের দিকে যাওয়ার সম্ভাবনা তৈরি হচ্ছে ফলে যদি তোমরা আসো অফলাইনে ফিজিক্যালি আসো তাহলে এক্সপেরিমেন্টটা দেখানো যেতে পারে তখন সেটা আমরা করবো আদারওয়াইজ এই চারটেতেই উই হ্যাভ টু কনফাইন আওয়ারসেলফ ঠিক আছে তাহলে আজকে শেষ করলাম এটা থ্যাংক ইউ
Thank you, sir.
Thank you, sir.
Thank you, sir.